one more thing that we're going to discuss here. It's what we call an ideal gas compared to a real gas. Okay. Now, gases have the properties they do and have all these relationships that they do because when they run into each other, they are hitting each other with so much speed that they just bounce right off. So their pressure is as if they're tiny little spheres flying around at some rate, and they bombard the balloon or whatever container they're coming in contact with, right? So their pressures are due to the fact that they're constantly moving and keeping that container at the given volume and the given pressure, all right? And because temperature is related to how fast they're moving, temperature is related to volume and pressure as well. And because the number of collisions that'll occur is related to how many gas molecules we have, all of these parameters are also related to N, which is the number of gas molecules. So what happens when this is a question for you, Camille, what happens when we begin to slow gas molecules down? What happens to them when they collide at a slower speed?
I would think that they don't connect. Does that make sense?
What do you mean, don't connect?
Like, if you're, like, coming at something really fast, then, like, you hit them really hard, and then, like, they bounce away. So if, like, they're slow, then they don't hit it as hard, and it doesn't.
Okay. They don't hit as hard. They might just kind of rub up against each other or something, right? They're not going to collide and bounce off very well, but they might run into each other. Now, if I just think about it, a chemical reaction, here's X in the gaseous phase, and we usually don't write the word slow in terms of what I'm doing in this chemical reaction or doing in this process here. But what happens, Camille, sorry, if I take X and I slow it down? What does it become? How does it change, or does it change?
I don't think it would change.
Well,
or does it?
Would you be surprised if it did that?
Oh, no, that makes sense.
Yeah, right? So, and if we slow it down even more, then what happens?
Solid.
Yeah, it becomes a solid. Okay? So that's not surprising to us. We know that if you take a gas and lower its temperature enough, it will become a liquid. And if you lower its temperature enough, it can become a solid. But if we think about what we mean when we say lower the temperature in terms of kinetic energy, we're actually just slowing it down. Why is it that when you take a gas and slow down the molecules, they become liquid, and you take a liquid and slow down the molecules, they become a solid? What's going on there? Well, what's happening is there is an inherent stability when you take, just like when you take atoms, two atoms, and bring them close together. If they can share electron density, then a bond will form and stabilize the two atoms. In the same way, if I have two, now these aren't atoms anymore, they're now molecules of a gas. If I take these two molecules of a gas and bring them together, if they come together fast, they'll just collide and go right away. But if they come together slow enough, they can interact in such a way that they can begin to share a little bit of electron density and stabilize their conditions a little bit, and that new stability is not as strong as a bond, right? Two atoms come together and they become bonded if they begin to share electron density. Two molecules, when they come together, they don't form a bond in between them, but they do form what's called an interaction between molecules, or an intermolecular interaction. And there is some stability. They stabilize each other a little bit, and because of that, it then begins to be hard to pull them apart, right? It takes energy to pull these things apart. Like it takes energy to go this way, from solid to liquid, right, to melt something, or from liquid to gas, to gasify, right, to evaporate something. It takes energy to do that, right? So there is some stabilization when molecules are allowed to hit slowly, gaseous molecules forming a liquid, and if you even slow down the liquid even more, they'll form a solid. So they're stabilizing each other. The same way two atoms come together and form a bond, two molecules can come together, not forming a bond, but forming what we call an intermolecular interaction. And we're going to use that a lot, that phrase, intermolecular interactions, moving forward through the next couple of chapters. So we want to be comfortable with how to say that, intermolecular interactions. There is a formula similar to perv-nert. See that here? PV equals nRT. Hopefully you can see that in this slide here, right? That deals with scenarios where instead of an ideal gas, conditions where the gas molecules just bounce around like little billiard balls on a pool table, in scenarios where the temperature is a little bit cooler, so the molecules come and they don't maybe stick together, but the gaseous molecules interact with each other and influence each other. And so it's not a completely elastic collision. You get more realistic scenarios, they call it a real gas, and we have ways to kind of adjust our perv-nert equation. And we won't be responsible for this, but we do want to begin to recognize the difference between ideal gas and real gas. Alyssa, anybody have any questions? Okay. So that's it for chapter 11, and we're going to move on to chapter 12 now, talking about these intermolecular interactions. Okay? All right. Intermolecular interactions or attractions are, whoops, let's see if we can try that again. Just a second here. There we go. Intermolecular attractions occur between any molecules, right? Any phase of molecules, any kind of molecules. Typically, though, our conversation about them is usually between solids and liquids, because if you're in a gaseous phase, those intermolecular interactions aren't strong enough to influence the properties of the gas. That's why they are in a gaseous phase, right? So these are generally intermolecular attractions or interactions between liquids and solids. And as we talked about, when a gas cools down, slows down the molecules begin to stick to form a liquid. So liquid is where the molecules have a degree of movement still, but when they're slowed down enough and become a solid, then they don't become absolutely still. There's still a significant amount of movement, but the molecules will move slower. Okay? Now, the interaction, the degree of the interaction between molecules depends on the property of the molecule itself. And that's not surprising. We know some compounds, like carbon dioxide, right? Carbon dioxide is a gas. It's relatively difficult, takes a lot of energy to make it a liquid, right? You have to cool it down quite a bit to make it a liquid. Whereas something like water, it's a liquid, and it's not very hard to make it a solid. You have to add in energy to make it a gas, right? So these two molecules, I mean, anything we choose, C6H12O6, that's our sugar, right, or glucose, a solid at room temperature. So this is a gas at room temperature, this is a liquid at room temperature, this is a solid at room temperature. The reasons that these are the states that they are has to do with their intermolecular interactions. Okay, so what we're talking about is two carbon dioxide molecules. Here's one carbon dioxide molecule. Here's another carbon dioxide molecule. Their amount of intermolecular interaction, how much they kind of stick together when they collide, decides what its phase is going to be at a given temperature. All right. So looking at this, here's gaseous, here's liquid, and here's solid. Which of these three, if they're all at room temperature, these are their phases, which one has more intermolecular interactions occurring between the molecules? All right, let's see. Whose turn is it? Landon, what do you think? Which of these compounds has the most amount of intermolecular actions that are influencing the molecules?
I would say the solid, the C6H12O6.
That's right. Those increased amount of intermolecular interactions are causing each one of these molecules to bind really tightly to each other when they combine at, this is a room temperature scenario. And again, why the difference? It's because of what we talked about before. If you look at the different atoms that are in the molecules and their differences in electronegativities, resulting in what we call polar bonds. Polar bonds. Now, what's a polar bond? It's a bond between atoms, like, for example, if I have a carbon interacting with an oxygen, right? You remember, Jace, is this a polar bond or a non-polar bond? Oh, Jace isn't here right now. Let's see. Harry? Polar bond or a non-polar bond? Oh, sorry, Jace. Go ahead. Okay.
That's polar, right?
It is a polar bond. And we have our electron density leaning towards which atom in this bond, Jace?
I'm going to say oxygen because that's more electronegative.
That's right. And we indicate that by showing a slight, or a D, delta negative here, and a delta positive there. Okay? So, the polarity in bonds is an indication of the likelihood of there being a increased intermolecular force between those bonds. Jace, did you have another question?
No, not bad.
Okay, I just saw your hand was up on your little guy, your little icon, so I thought maybe you had a question. But okay, so this polarity in a bond is called a dipole. We didn't refer to it a lot in Chem 105 as a dipole, but because of one of the types of intermolecular interactions, we'll call it a dipole moving forward. And again, dipoles or polar bonds within molecules may or may not end up resulting in the molecules that are polar. Okay, I'll say that again. Polar bonds or bonds with dipoles in them within molecules may influence the molecule to be polar. All right, doesn't always, but it may influence the molecule to be polar. And Harry, does carbon dioxide have polar bonds in it?
Yes.
It does have polar bonds, but then why is it a non-polar compound?
Because it's symmetrical.
That's right. So to make a polar compound, you need polar bonds, but you also need to have an asymmetrical molecule like water here or ammonia, such that the pole of electron density is actually shifting to a different plane or a different side of the compound. Okay, so that's hopefully all that portion about polar bonds, electronegativity, polar bonds, and polar molecules. Hopefully all that's relatively, is a little bit of a review. All right. Okay, now we're going to start to introduce the different kinds of interactions. Actually, that's a good place to stop. Let me